Let's get going. Can we see that? Today we're going to continue talking about rstanarm and extend what we were talking about on Tuesday with linear models to a slight extension that's more useful for a lot of models in the social sciences, the so-called generalized linear regression models. So just jump right into the obligatory disclosure. Work at Columbia. Columbia is and has been and recently did get a grant to develop STAN. Also have an LLC, and according to Columbia University policy, that creates the appearance of a conflict of interest that has to be disclosed before talking about anything related to STAN. So the examples from the reading, which if some of you still have not gotten, I have some more copies of it here, are available at Aki's GitHub site in one of his repositories. So here is one of them using the so-called Kid IQ data set, which is also available in rstanarm, but it's on the website along with code similar to this. So I'm just going to load the rstanarm package, tell R that I want to use all the cores that are available on the machine. I put the Kid IQ data set in order of the mother's IQ. That's just for plotting purposes later. Anyway, the point of this relatively simple model is to try to get at the relationship between how well a baby or maybe other small child does on some standardized test as a function of the baby's mother's IQ and whether the baby's mother graduated from high school. So mom HS is a dummy variable indicating graduate from high school. I want to estimate a model that has the interaction of those two things. So we used Stan LM last time. You can also use Stan GLM for outcomes that are continuous. So the first line here basically implicitly specifies the likelihood function that is being used by Stan when you estimate this model, where the outcome is a function of the predictors, possibly with interactions. You have a data frame saying where all these variables are, and family is Gaussian to say that you want to use a normal likelihood. The LM function, the Stan LM function that we talked about on Tuesday, only require that you put in prior mode or prior median for the R squared before you see the data. Stan GLM is a bit different, a bit more conventional, but it can be harder when you have lots of predictors. In this case, we just have 2 or 3. But with Stan GLM, you put priors on the coefficients and the intercept and possibly the standard deviation of the errors. These all have default values, but in the case of IQ, you should be able to put a pretty good prior on the intercept because IQ tests are constructed to have a mean of 100 and a standard deviation of 15 marginally. Now, what all of the functions in rstanarm that fit models do, it's going to internally center your predictors. So the intercept can be interpreted as the expected value of the in a linear model can be interpreted as the expected value of the outcome for someone with average values on the predictors. But in a linear model, the person with average values on the predictors is going to have the average level of the outcome. So technically, you should be sort of specifying your prior on the intercept conditional on the average person, but that's not so much different from just specifying a prior on the intercept marginally, which we know from the construction of IQ tests that they have a mean of 100 and a standard deviation of 15. Also, with prior, you put priors on the coefficients. Here, we're just going to use normal priors with the default values. There's some weakly informative stuff going on. I specify false for auto scale, which is to say don't. So by default, Stan is going to interpret the scale arguments to these priors as pertaining to standardized coefficients. So in terms of standard deviations. But if you say auto scale equal false, it tells Stan to not mess around with that, to just interpret it in the regular units, which is what we want here. But usually it's easier to think about a prior scale relative to standardized coefficients that have not only been centered, but have a standard deviation of 1. Stan, or internally to rstanarm, it does center. It doesn't actually standardize the predictors, but it does scale the priors by the reciprocal of the standard deviation if auto scale is true, which is the default. And then finally, specify the argument QR equal true. This is another non-default argument. It's not talked about in the book, but actually you should be specifying it most of the time. If you're just going to use sort of weakly informative normal priors on the coefficients in a model like this, then you're better off specifying QR equal true, which is not the default. We'll explain why as we go along in later weeks, but it helps to get better effective sample size by reducing the correlations in the parameters of the posterior distribution. Yes?
What are the priors and coefficients?
Normal.
0 or 1?
It's not. It is normal with mean 0. The standard deviation is not 1. It's like, I think 2.5 or something like that. But anyway, it's intended to be a weakly informative prior on coefficients. Other questions about the syntax of it? But basically, it's the same syntax as you would call with GLM. You just put stan underscore on the front of it, and then the first line is the same. The only thing different, you can, if you want, add information about the priors, but the defaults tend to work pretty well, except for QR equal false is the default, and it works better if you do QR equal true. But that's really just a question of getting a good effective sample size. So we estimate this thing, whatever, then we print it out, and then we get the posterior median, posterior standard deviation, a robust estimate of the posterior standard deviation for each of these margins. Now, I said before that when Stan or rstanarm estimates one of these models, it centers the predictors. However, when the results come out, it decenters the intercept so that the intercept pertains to non-centered predictors in order to correspond to what GLM does. So that's why this is now, very different from what you specified in the prior, but that's okay. It's just, it sort of estimated it was centering and then shifted the estimate of the intercept over to undo the centering after it was done. We get, posterior median of the coefficient on did the mother graduate from high school. This is for the case where IQ is 0, so it's not particularly realistic to say someone with an IQ of 0 would be graduating from high school, but anyway, that's just what you get with interactive models, and that's why interpreting these things absolutely is not particularly relevant. We get a slope of 1 on the IQ variable among mothers who did not graduate from high school, so there's sort of a 1-to-1 relationship. And among mothers who do graduate from high school, the slope with respect to the IQ variable is 1/2 lower. So for a total of 0.5. And then the estimated standard deviation of the errors is 18. Most of these are estimated reasonably precisely in terms of how large the median is relative to the standard deviation. Again, you can work with the draws directly. You're not confined in terms of your inferences to just medians and standard deviations or anything like that. You can work with the raw draws, or there's a variety of convenience functions in rstanarm with posterior intervals and whatnot, where you can look at different aspects of this posterior distribution, which is basically just a list with a whole bunch of draws and some other stuff in it. So questions on this output or this syntax input? Oh, yes.
So just trying to interpret this. So like on my view that the MADs. The MAD stands for the median absolute deviation.
Median absolute deviation from the median, and then it's scaled by this 1.42 number that makes it a consistent estimator of the standard deviation if it's normally distributed. So it's sort of a robust estimator of standard deviation. Okay, so if this were, say, like 2, the MAD-SD for MOM-IQ, would that mean we basically have more error and imprecision in the estimate than there's more noise than not? Would that be like an appropriate interpretation? I think that's too close to the frequentist interpretation, where you would say, like, is the estimate 2 standard errors away from 0? But loosely speaking, yes, the higher the standard deviation, the more imprecision in the coefficient estimate. But again, with these interaction models, like looking at the marginal standard deviation isn't so relevant anyway, because there's a nonlinear relation or different slopes relationship depending on whether you graduate from high school. So over interpreting any of this, I think, is not really the Bayesian way. We're going to show in the next couple slides how you can sort of see that relationship better. Okay, so this is a plot. I think there was one in the book. If not, there's a similar one in the book, or it's online, but just taking these posterior medians, -11, 51, 1, -0.5, whatever, and using it to construct lines. So here the dark line is the estimated relationship among mothers who graduated from high school, or and then the gray line is the estimated relationship among women who did not graduate from high school in terms of the sensitivity of how well their kids do on the IQ test as a function of the mother's IQ. So you can see these lines. It's by construction of the model, a linear relationship. We also have black and gray points to show the actual data values. And so you can see from the points that the lines are at best pertaining to a rather noisy relationship between the baby's IQ and the mother's IQ. But it is sort of positive in both cases. It's just less positive in the case of women who graduated from high school. But a plot like this, which is sort of a plot that you would make if you had just frequentist point estimates, isn't capturing the uncertainty in really reflecting in the model that well. All you can sort of say is, well, the points are not that clustered on their respective lines. So in my opinion, a better way to plot something like this can be done with the base plot package, which we'll be talking about more, by taking the output of the posterior predict function. So this is what my model predicts the baby's IQ would be for various levels of the mother's IQ. And I put that as my column names in order to make this plot come out in order. And then I call the MCMC intervals function on that PPD4, which is the output of posterior predict, passing in the model fit function that I obtained 2 slides ago. So posterior predict will return a matrix that is S by N. So it has S rows and N columns. Each of the rows pertain to one iteration of the Markov chain. Each of the columns pertains to one observation in the original data set, or if you give it a new data set for out of sample predictions. Anyway, this is what the model predicts, fully reflecting the uncertainty not only in the coefficients, but also in the fact, like, even if you knew the coefficients, the baby's score on IQ test has a lot of randomness in it, depending on like whether the baby is having a good day or a bad day, or, you know, whatever. Babies are not real predictable. So there's going to be, you know, noise. If you had, you know, literally the same baby take the test 2 days in a row, they would get totally different scores, you know, a lot of the time. So there's fundamental noise there, and there's uncertainty because we don't know the parameters in this model, and there's uncertainty. We don't know that this is the right model, but let's just sort of put that aside for now. This plot fully reflects our uncertainty both in the coefficients, which we don't know that well, and babies, which we know to be noisy in their performance on tests. Anyway, MCMC intervals outputs a ggplot object, so you can add more ggplot syntax on that. So this plus is not like addition, it's add a layer or add an attribute to the plot before you put it up on the screen. So I flip around the coordinates and change the axis labels and whatever. But anyway, the point that I wanted to convey is that this plot does a better job of reflecting how fundamentally uncertain we are about the baby's IQ as a function of the mother's IQ and whether she graduated from high school than this one, which just shows the line. This one shows 50% and 90% intervals around that line, both for the women who did not graduate from high school, which is like that, and the women who did, which is a line that is less steep. So the dark blue bands are 50% credible intervals around the median, and the lighter blue bands are 90%. You can change all of those when you call MCNC intervals. But anyway, this is sort of saying, well, sure, there seems to be somewhat a linear relationship, but the 90% intervals basically span like more than 60 or so, usually, IQ points for the baby. And a difference of 60 is like 4 standard deviations. So basically, given the mother's IQ and whether we went to high school, we can't, like, it. The baby could be a genius, the baby could be like kind of dumb, but both of those are consistent with the model. And so this one really doesn't have enough predictors and other things that you might want to, you know, put in a model of babies to, you know, really give you the ability to say anything about an individual baby as a result, you know, based on their mother's 2 characteristics. Although perhaps, you know, you could say something about, for babies as a whole, there's like positive relationships going on with their mother's IQ and whatnot. But I think this one, which fully reflects the uncertainty both in the coefficients and in the babies, is a more honest depiction of how like not great this model is. Or even if this model was great, it's not super useful for applying it to an individual baby because there's so much noise going on here. Yeah.
So again, probably relying too much on our frequentist background, but when we put confidence bands on a regression line, they tend to shrink towards the middle where the weight and density of the data is and expand on the fringes. And I'm noticing that's not happening here. I would expect there would be more uncertainty near the edges. So I'm expecting wider, we call them credibility bands, I think.
You will sometimes see something like that in nonlinear models, but for a linear one, you're basically saying, you know, extrapolate the lines out all the way in both directions. So they tend to have similar widths going forward, but you can see like there's some that have these like narrow ones, and then some where the bands are much wider. There are way more. I should have colored them differently, but I think there's more women who graduated from high school than there are women who didn't graduate from high school. And so, or maybe the other way around in any particular data set. And so the estimated coefficient on, when you sort of combine the interaction terms and whatnot for, let's say, women who graduated from high school is more precise than for women who did not graduate from high school. And that's why you see sort of two levels of credibility intervals, the like awfully bad ones and just only kind of bad there. But when we do Logit models, yeah, you will see this sort of weirdness at the edges of the space there. Do you have a question? No. Other questions? Okay. So this is sort of consistent with what I was saying last time. Don't get too caught up on this. Even though this looks more analogous, it's not even analogous, but it looks analogous to frequentist output. With frequentist output, you're just kind of stuck with these coefficients and like you test for significance or something like that. But with the Bayesian approach, because you have the ability to push the predictions or the whole posterior distribution through the model to obtain predictions, you can actually make these plots and these things like that in terms of observables, like, baby's IQ score, and sort of say, how does your predictions change as the mother changes, or, things like that. And so I think that is a better way to convey stuff, but it's also an easier way to convey stuff to people who didn't take the class, aren't familiar with Bayesian inference, certainly aren't familiar with Stan, probably don't even really know how to use GLM that well. But if you can just show them the picture, then they say, oh, okay, like smarter mothers, smarter babies, but there's a lot of uncertainty going on here. Questions? Okay. So another thing that people often worry about, well, okay, I specified some priors, or maybe I took the defaults, whatever. And then somebody asks you, well, how do I know that your results aren't just like super sensitive to the priors that you specified? And they have kind of a hard time articulating what the priors like were. It's not even totally obvious because we're doing a lot of tricks behind the scenes and stuff like that. But one thing that you can always do is call one of the models with the prior underscore PD equal true argument. This just draws from the prior. It doesn't condition on the observed data. So you get back a posterior object, but one that didn't condition on the outcomes. It just conditioned on the information you supplied for the priors. So now you get this distribution that, again, you can plot the characteristics of to say, like, what's going on with it. So the update function, when applied to a object produced by rstanarm, we'll call it with the same arguments, except you can change or add new ones. So I add the new argument prior PD equal true to call the same with the same data and all that, but not conditioning on the data. So just drawing from the priors. Then I can make a plot of that basically prior distribution. And with the shifting and all that, it comes out like this. So certainly have diffuse priors on the high school variable. Did the mother graduate from high school? Probably too wide, especially considering like there's a lower bound to the test score. Like you can't get 250. So if anything, these are like too diffuse. But it's a whole lot better than doing like an improper prior, which is to say like all real numbers are equally plausible. By contrast, the ones for the mother's IQ and the interaction between mother's IQ and high school, these are much smaller. Like the 90% interval doesn't even make it outside the median dot here. So much smaller defaults there. And then the standard deviation on sigma, it's actually constrained to be positive. So we have this asymmetric distribution here, But again, it goes out, its 90% interval goes to, 50 or something like that. So the idea of priors in rstanarm with the defaults is certainly to be only weakly informative. But even that does help stabilize the performance a lot. Yes.
How is the prior on mom IQ determined?
It's complicated. So you're saying, okay, normal with 0 and some standard deviation, but the QR thing makes it not obvious at all because it's actually doing a transformation to your predictors. And then when you see this, it's a result of untransforming the transformation that it did before, so that it's saying that your priors are like with respect to the original untransformed, uncentered, unscaled, none of that predictors. And so that's why the plots like this are necessary, because honestly, like, you really have to read the documentation and the code in order to get a full explanation. And we haven't started talking about matrices or anything. So the saying, oh, it uses a QR decomposition doesn't really make a whole lot of sense yet. We will learn, properly speaking, what this means and what it does later, because it's an important technique. But that is the reason, because of the internal like scaling and rotating and stuff like that, it's sort of, there's a disconnect between what you put in and what the priors actually are sometimes. So that's why it's good to look at the plot, because that's what was implied for what you gave it. And if that is like too diffuse, which it certainly is for the mom high school thing, then maybe change the scale factor on that normal prior to be something less.
Should we be worried that there's no kind of uncertainty around our prior?
There is some. It's just you can't see it. It's less than the width of this dot. But in this situation, I actually think it's probably before seeing the data or the baby or whatever, is there a 1-to-1 relationship? That'd probably be about as strong as it could be between the mother's IQ and the baby's, something around that. And so certainly values that are like between -5 and 5 are consistent with the width of that dot. So yeah, I don't think it was that horrible. Other questions? Oh, yes.
What would give you pause here? Or like if you were to, what's the point of doing this, I guess? Like what would you find?
Yeah, so my takeaway from this is like the priors on the intercept and did the mother graduate from high school are very weak. They could probably stand to be narrower. But this turns out to be like not horrible because we have a reasonable amount of data. And so we can estimate those in the posterior distribution with, in frequentist terms, it's like 3 times the standard deviation. So it didn't turn out horrible, but you want to look at these things, and maybe what jumps out at you is like there's too much imprecision here and not enough on these to be reasonable with your theory about childhood development. But your theory about childhood development may be different from somebody else's. So look at them, see what's up. Okay, so that was a linear model. The outcome was not totally continuous, but it was mostly continuous for our IQ test. Now we want to start talking about Logit models, which are appropriate for the case when the outcome is Bernoulli or binomial, as long as the probability of success is constant within whatever group of data that you're specifying on. So again, we have this thing where the STAN program on the left is going to be drawing from the prior predictive distribution. The STAN program on the right in blue is going to be sort of for the corresponding model, how I would specify the logarithm of the kernel of the numerator of Bayes' rule if I wanted to condition on outcome data that I had observed. The one on the left is sort of what you believe the outcome to be before you see it on the basis of your priors and in conjunction with the model. So this is going to return a matrix of S rows and N columns. S is the number of simulations, N is the number of observations that we have in terms of rows of X. And then A-log, A-scale, B-log, and B-scale all pertain to the normal priors that I'm going to be using for the intercept and the slope in this Logit model. So I allocate those. I center my predictor variable. This obviously can be generalized fairly easily to the case where you have more than one predictor, but you're going to have like more slopes and more priors and all that. So for each of the simulations that I want to do, I take a draw of the intercept from a normal distribution with some prior mean and some prior standard deviation. I take a draw from an independent draw from a normal distribution, maybe with a different mean and standard deviation, to get a realization of the slope. Take alpha and beta, the intercept and the slope, multiply the slope by the centered coefficient. I get a vector of size n, which I will call eta. So you may be accustomed to interpreting eta as the log odds of success in a Logit model. That's a valid interpretation, but not one that I think is the most useful in the social sciences. And here's an alternative one. So we loop from the first observation to the nth observation, each time constructing a utility, which is equal to the nth value of eta, so the value of eta for the nth person, plus a random draw of an error from a logistic distribution, particularly a standard logistic distribution, one that has a mean 0 and a scale of 1. So if we think of that as like the utility for the difference between whatever success is and failure is, or something like that, that we might estimate a Bernoulli model for. If we think of this as the utility difference, then we're going to say, well, y is 1 if utility is positive, indicating there's a higher utility for choice 1 than for choice 0. And if utility is negative, then the person chooses whatever choice 0 is. So we just have this indicator function. And so when we observe these zeros and ones, it's basically saying we observe the sign of the person's utility difference between those two things, but we obviously don't observe the utility directly. And in that interpretation, beta is sort of the sensitivity of utility to the person's X predictor. Anyway, when we're done with both of those loops, then we can return our S by N matrix of prior predictions. So taking realizations from our priors, using those along with some sort of distribution for the error in order to get predictions for the outcome before we see it. And so this, again, is going to reflect our uncertainty, both in the coefficients and even if we knew the coefficients, there would be sort of fundamental noise in outcome, like due to measurement error or inconsistencies in humans or whatever it may be. So before I go to the blue version, are there any questions about this code for drawing from the prior predictive distribution? So the distribution of the observables that's implied by our whole model, inclusive of the priors. Questions? Okay. So in reality, we're going to have some observed data on zeros and ones in addition to the X's and whatnot. So reality is like we get one row of this matrix, one value for each of the n observations. It's either 0 or 1 for the outcome. And then when we want to update our beliefs to get the posterior distribution, we want to condition on those outcomes that we observe. And to do that, we're going to need to give Stan a kernel function in log units. So this is going to return a scalar for the logarithm of the numerator of base rule. It's going to take as arguments the proposed values for the intercept and slope. The same stuff as before that we needed to specify our priors. But it's going to also take an integer array called y, which is our observed outcome, 0 and 1, and we have n of those in addition to our vector of values on x. So remember, this kernel function is a function of the parameters conditional on observed data, whereas the version on the left here was really to generate from the distribution that we anticipate the data to be before we actually collect the data. Anyway, it's a lot the same. So again, we center the predictor variable. Instead of drawing from a normal distribution, I'm going to evaluate the logarithm of the normal PDF at the proposed values of alpha and beta given my location and scale parameters to those normal priors. Those are just going to output, scalar values. I save them as P and Q just to use later. So these are values of the log density for alpha and beta given the A log and A scale, B log and B scale, etc. Then I form eta again using the intercept and slope and my centered predictors. And then at the end, when I return, there's no loop or anything like that. It's just we're returning the sum of the log prior densities and the log likelihood. So we've got P and Q from the priors, and then there's a likelihood statement saying use a Bernoulli likelihood with a Logit link function for the outcomes evaluated at or of the utility values which are captured in eta, utility being a function of the intercept and slope that I'm estimating. And so this is the function that I would need to specify in order to tell Stan, okay, let's condition on these outcomes, update our beliefs about alpha and beta from where they were originally, which is reflected by these normal priors on each of those. Questions about that or about the difference between the left and the right version or anything? Okay, so what does this Bernoulli Logit LPMF do? Okay, so what's the logarithm of the Bernoulli PMF? Logarithm of Bernoulli PMF?
Divided by minus E times
No. Okay, what's the PMF of the Bernoulli distribution? Success probability raised to the y times failure probability raised to 1 minus y. There's no division or anything like that. Okay, then we take the logarithm of that. So again, mu is the expectation. You could write it as p or pi or something like that for probability, but the expectation of a Bernoulli is the success probability. So if we wanted to convert this to like a log likelihood function, we take the logarithm of that expression, so it's y, which again is 0 or 1. That's the sample space of a Bernoulli outcome, times the logarithm of mu plus 1 minus y times the logarithm of 1 minus mu. So that's our log likelihood function. And then what's the conditional distribution of utility in a Logit model? So if we go back to this, we're saying, okay, utility is equal to eta, the nth value of eta, plus an error that has a standard logistic distribution. And we're saying, well, the outcome is a success if that utility difference is positive, and failure if that utility difference is negative. So what would be an expression for the probability of success if utility is logistic with expectation eta and scale 1 under this process here? So if this is what we think our model is for the outcome, what will be an expression for the probability of success?
It's a little bit hard to read when it's highlighted.
Okay. No highlighting? Does that help? So really what we're asking, what's the probability that utils is positive? That's the same as saying, what's the probability that y is 1? Right? Okay. So how would we express what's the probability that utils is positive in terms of probability distributions? So in general, how would we express what's the probability that some random variable is greater than 0? Pretty close, but I want you to say it. What's the probability that something is greater than something else in terms of functions that we've learned about? Okay, let's call that right. 1 minus the CDF evaluated at this case 0. So 1 minus f 0 given eta in scale of 1. So this piece here is the probability that it's less than 0. 1 minus that is the probability that it is greater than 0. So just using the complement of the CDF. Now, it can be shown for the logistic distribution, this is often the case for symmetric distributions, that 1 minus the CDF of 0 given eta is equal to the CDF of eta given 0. So if eta were the random variable and we evaluated it at the standard location 0, scale 1, we get out the same number. And as we talked about before, the standard logistic CDF is 1 divided by 1 plus e to the negative eta. So the success probability is given by this expression here. And eta is a function of x, namely alpha plus beta times x. So that's how we work that out. If we combine those and substitute that expression for mu, then we get something like this when we simplify it down. And the reason why we have functions in Stan like Bernoulli, Logit, LPMF, LPMF, PMF, and stuff like that is because a lot of times when you take the logarithm, you can simplify it down. So maybe you can evaluate the function faster. Maybe you can evaluate it with more numerical stability, etc. And so, you know, it's faster to just calculate the logarithm of 1 plus e to the negative eta once and use it twice, so save some time there. It also does some tricks with like logarithms and sums of exponentials and stuff like that in order to avoid numerical overflow when doing e raised to the power of anything. You're quite likely to get numbers that are too big for your computer to represent. So you need to do some tricks to keep everything in terms of log units rather than taking the logarithm of some giant number that could overflow. So that's all what's happening, you know, behind the scenes with Bernoulli underscore Logit underscore LPMF. And it takes a whole array of outcomes on y and a vector of utilities on eta and returns a scalar, which is the sum of the log likelihood contributions that are independent across all of the observations that we have in our data set. So this p plus q plus Bernoulli Logit LPMF is a scalar, and all we have to do is basically normalize that But in order to do that, we would have to integrate over alpha and beta, so a double integral, in order to get the denominator of Bayes' rule. Stan doesn't mess around with numerical integration or anything like that, but equivalently draws from the implied posterior distribution, so you get draws of alpha and beta and any other parameters conditional on the data. So that's that. We can expose the prior predicted distribution function to R, give ourselves, some arbitrary x values, etc. We can put in some stuff that may be, consistent with our priors, and get back a S by N matrix of zeros and ones, which are the predictions implied by our model. And then we can sort of, plot the column means of that, which represent the probability, to see if this seems like a reasonable function if, this were like substantive x and y data. So in a situation like this, does this curve adequately represent what you believe about the, whatever data generating process this represents? And so, as Nick was saying earlier, sometimes with the endpoints of these things, you can see, the nonlinearity takes hold. But for the most part, between like 25 and 75, whatever those are, there's a pretty linear relationship between the predictor and the success probability. It only, starts to flatten out as you get to more extreme values. Extreme values being like 0.7 and 0.3. So this might be a reasonable specification if you think, everyone's probability is pretty well interior. And there's not anybody who has like success probability of 0.99 or 0.01, something like that. But if you did think there were such people, then you would need priors that have more dispersion to them, or maybe to use a distribution for the errors that has heavier tails than the logistic in order to get those more extreme probabilities. So this is what Patrick was saying, an example of how you can check to make sure that what you think you put in is reasonable actually implies reasonable predictions for the observable phenomenon that you're just about to collect data on, condition on, and use like the blue version of this to update your beliefs about the intercept and the slope in this Logit model. Questions about that? Good. All right. So I forgot to say this last time. This is just side note, weird R thing that you need to take into account. So you're used to seeing dummy variables just coded as like zeros and ones relative to some baseline category that is omitted. That's the way like Stata does things and way like everybody does things in social science. However, in R, if you have an ordered factor, it doesn't just make a bunch of dummy variables that are 0 and 1 relative to a reference category that gets omitted. It does something called Helmert Contrast. I don't even really know what Helmert contrasts are. I've literally encountered 0 people who were like, I want Helmert contrast. But somehow it's the default in R. So you need to do this once to change the encoding for ordered categorical variables, ordered factors, when you use them as predictors. By just executing this line once, it'll create this file called .rprofile, which is read when R starts up. And it's telling you for both the unordered case and the ordered case, I want treatment style contrasts, which are just dummy variables relative to a reference category that gets omitted when doing regression models. Otherwise, you'll see all kinds of weird Helmert business going on, which gives equivalent fit, but a different interpretation. And I honestly don't even know what the interpretation is. So I'm not even going to mess with it. I put this on all my computers, but I forgot to say it last time that you should do it with yours as well. And that comes into play when considering this Logit model that we're going to do based on polling data that was taken like a week before the 2012 presidential election between Obama being reelected and Mitt Romney. So that data set is on Canvas. You can load it up. When estimating a model like this, where all of your predictors are categorical, you can go from Bernoulli to binomial just by summing up the number of successes within each configuration of the categorical variables. And so we can do that rather easily with the dplyr package that most of you are probably familiar with. So this just says like, throw away the NAs on the outcome, which is the want to win variable, group by all these categorical variables, and then sum up the number of people who favor Romney, and then the converse of that, or the complement of that, is the number of people who favor Obama. And then we can use stan GLM. If you're estimating a binomial model, you need to give it both the successes and failures, so it doesn't matter how you code it, but in this case, 1 is for Romney and 0 is for Obama. This just means use all the predictors in the data set, all of which are factors, but age and income are ordered factors. And then, okay, that's the data set. And then family equal binomial, to say you want to use a binomial likelihood, link equal Logit, because this is going to be a Logit model, and then QR equal true, so we get better effective sample size. It runs pretty quickly. You get output that looks like this. So these are coefficients for the dummy variable on each of these categories, and then the intercept corresponds. Corresponds to someone who has 0 on all the dummy variables. So that would be someone who lives in the Midwest, is female, rural, young, and poor. That's what the intercept pertains to. And then everybody else is just shifted relative to that. Okay. So again, we get posterior medians, posterior standard deviations that are more robustly estimated. Great. Okay. All of this pertains to, utility for voting Romney versus Obama. But it's still, that's sort of in arbitrary units. So we want to see how we can do that better on the next slide. Also, we'll come back to this in a few weeks. So you can see there's sort of a upward trend in the posterior medians as you go from poorer people to richer people in terms of their support for Romney. But there's not that many rich people in the, it's for older people, yes, but also for rich people, there's a trend in both cases. But there's not that many people earning 150,000 or more in this data set. And so that coefficient is estimated pretty imprecisely. We could do better, although not in rstanarm currently, by saying, okay, these dummy variables for all the income categories have a trend to them, as opposed to just saying they're all like independent normal priors on them, which would probably be substantively reasonable, both for income and for age, based on what we know about older, richer people and how much they love people like Mitt Romney. But anyway, so other than that, the coefficients are not what you want to be interpreting, because there's a nonlinear relationship between all of these predictors and the probability that they vote for Obama. So you can do something like this, which may not have been the most effective way to present this information, but it does achieve my goal of putting as many ggplot things on one slide as I could to illustrate you could do some subset of all of this. So the tidyBayes package utilizes this sort of tidy outlook on life in the context of Bayesian posterior distributions and visualizing them. So I want to throw away the people that had 150,000 income because there was like 4 of them in the data set. So those were estimated totally imprecisely. The add fitted draws gets the posterior distribution of mu in a Logit model, so the success probability. And then you can pass it to ggplot, you can pass it to ridges, do all this stuff with the colors. You can do different ones for region and gender, and facet rapid, so you have different age categories over here, different income categories over there, and you see a density plot for this or that type of people in terms of what is the probability that they would be supporting Romney on the horizontal axis here. So if you know the sort of ggplot way of doing things, and you know the tidy format of data frames for doing things, you can utilize those to make like all kinds of plots that are actually, there's too much going on in this one, but you can make really nice plots. That's kind of the bottom line for this. And you can look in the documentation of tidybase. There's a ton more things you could do, and we'll see some of those as we go along. So both tidybase and baseplot, they're different, but they all utilize ggplot2 objects for plotting that you can then, configure how you want the plot to look, however you want. Okay, so that was a Logit model. Probit model now. So Probit models are very common in econometrics. Logit models very common everywhere else, even though they both pertain to Bernoulli or binomial outcomes. And if you compare this to what we did before with the Logit model, really the only thing that I changed was this, to change the error distribution from standard logistic to standard normal. Now I have a Probit model. In terms of, okay, if I want to condition on the data, how would I do that? Only thing I changed here is instead of doing Bernoulli underscore Logit underscore LPMF, whatever, it's now Bernoulli y given phi of eta to map, to use the standard normal CDF to map the utility values given by, or the expectation of utility given by eta to the 0-1 interval, and thus be appropriate for success probabilities. So really changing like one line of each of these went from Logit to Probit, Probit being more common in econometrics. They're extraordinarily similar. People get caught up in the differences because the coefficients have different scales and stuff like that. But really, if you just focus on the success probabilities, you probably are not going to even really notice the difference between Logit and Probit models. But in some cases, it may be more natural to use one or the other, but more likely for some audiences, they may think one is more natural than the other, in which case you should probably use that one. But not a whole lot needs to be changed in order to accomplish that. And if you were doing this with rstanarm, instead of doing binomial link equal Logit, you would do binomial link equal Probit in quotation marks. Now you have a Probit model. That's kind of all that needs to be said about that. But we've sort of indirectly or from examples stumbled on a more general approach to modeling known as generalized linear models, or GLMs. So the sort of general statement of a generalized linear model consists of basically 3 pieces. So before you see the outcome data, pre-data statement, the outcome is going to have some probability distribution. And for frequentness, this has to be a distribution among the exponential family, which includes the exponential distribution and the normal distribution and a bunch of others. So a lot of familiar distributions there. For Bayesians, it doesn't necessarily have to be from the exponential family, but it often is. That probability distribution for the data before you see it has some location parameter to it. which for frequentist absolutely has to be the conditional expectation of the outcome given the predictors. For Bayesians, again, it doesn't necessarily have to be, but typically is. And then the third piece to it, or fourth, or third out of four maybe, you have to specify a one-to-one function known as a link function that maps from the conditional expectation mu as a function of the predictors x to the so-called linear predictor eta, which is also a function of x. So this link function needs to be one-to-one, bijective, all that, so you can invert it. So it's usually more natural to think about the inverse link function going from eta to the conditional mean of whatever distribution you're using for the outcome data before you see it. And then, okay, what's eta? Eta is known as the linear predictor. For frequentists, that has to be a linear function of the parameters. It can be a nonlinear function of the x's, but it has to be a linear function of the parameters. So you can include interactions, polynomials, stuff like that, as long as eta remains a linear function of the coefficients. For Bayesians, again, that's not strictly necessary that it be a linear function, but the one that we've done so far have been. It's a convenient enough starting point. So generalized linear models have these four components: a distribution for the outcome. That distribution is going to have some conditional mean. There needs to be a function mapping from the conditional mean to the linear predictor that allows you to invert it, go the other way from the linear predictor to the conditional mean. And then the linear predictor is a linear, if you're Bayesian, maybe a nonlinear function of the predictors. And once you specify those, in addition to like what the predictors are, then you have a likelihood function. And then if you're Bayesian, then there's going to be priors, and you're going to draw from the posterior distribution. If you're frequentist, there's no priors. You just find the mode of the likelihood function, and that's your point estimator. And then maybe calculate the curvature around that mode, and that what gets you standard errors and confidence intervals and all kinds of stuff like that. But for both Bayesians and frequentists, the sort of setup of the likelihood function is mostly the same. Although if you're Bayesian, you can get away with relaxing some stuff about, it has to be exponential family, or it has to be conditional mean, or it has to be a linear predictor, stuff like that. But for now, we're just going to sort of, even though we're going to estimate the posterior distribution of these in a Bayesian fashion, we're going to specify this the same way frequentists would and sort of adhere to their restrictions on things. Any questions about that? Or maybe it's easier to just look at a table of these choices from the examples that we've done so far today. So the first one with the kid IQ thing, that was just like a linear model. So a linear model is a special case of a generalized linear model where the inverse link function is just an identity function. So mu is equal to eta. There's no nonlinear transformation or anything going on there. So special case of a generalized linear model with identity inverse link function. And if we were doing this in Stan, which we did, we would use the normal distribution for the outcome, which has some conditional mean mu. And in this case, or in that case, it had this extra parameter known as an ancillary parameter, sigma, for the standard deviation of the errors that we also are going to estimate. For a Logit model, that was with a Bernoulli or a binomial likelihood, and the inverse link function is known as the inverse Logit function, where mu is equal to 1 over 1 plus e to the negative eta. So we talked about that. With the probit, all we're doing is changing the inverse link function. We're leaving the likelihood pre-data distribution of the data the same. It's still Bernoulli or binomial, but we change the inverse link function to be the standard normal CDF rather than the standard logistic CDF. And now we have supposedly a different model, but it's actually very similar. We're going to talk about Poisson and negative binomial next. Also, or at least the Poisson is. for count outcomes. And the inverse link function we're going to be using in that case is mu is equal to e to the eta. And we actually use that same one when we talk about a negative binomial model, which has an additional ancillary parameter phi. So negative binomial is an example of something that's only a generalized linear model if phi is known, if you're a frequentist. From a Bayesian, you can estimate phi and nothing really changes. But these restrictions that frequentists impose on themselves, it's in part for reasons of interpretability, but those models aren't super interpretable to begin with. It's mostly because in order to derive the sampling distribution of the maximum likelihood estimator across data sets that are drawn independently from the same population and have a size n, in order to work out what that distribution of the point estimator is across data sets, they need to make stronger assumptions than what Bayesians do, and even still, they can really only get these things asymptotically as n goes to infinity. With Bayesian, you can relax a lot of this stuff. You're estimating it using Stan, either way. So you can estimate the ancillary parameters, and things don't have to be totally linear or anything like that. But these ideas of, what's the pre-data distribution of the outcome look like? What's the conditional mean of that distribution? How is the conditional mean related to the linear predictor? And then what goes into the linear predictor are really the essential elements of specifying one of these generalized linear models, or at least the likelihood function for one of these generalized linear models. And then the question becomes, okay, if that is sort of your likelihood part of your model, what would be reasonable priors on the exogenous unknowns in a model like that, which, intercepts and slopes, stuff like that, that we're talking about today. So questions about the generality of generalized linear modeling? It's really a whole sort of framework for doing regression modeling that is, obviously emphasized in the reading for this week. Questions? Okay, so let's do some of these count ones. So sort of the point of seeing Logit models and Probit models and Poisson and all that in terms of generalized linear modeling framework is that when you start to write down the posterior predictive distribution, or a function to draw, the prior predictive distribution, or a function to evaluate the logarithm of the kernel of Bayes' rule, not a whole lot changes, even though the outcome is different. In this case, it's a count, unbounded rather than like success or failure or anything like that. But when drawing from the prior predictive distribution, all this stuff is the same until I get to this line. So instead of mu being, whatever it was for a Logit model or a Probit model as it relates to eta, now mu is equal to e raised to the power of eta. So that's my conditional mean function. And I want to draw from a Poisson distribution in order to get draws from the prior predictive distribution of a count outcome. That might be appropriate from a Poisson. And then over here, again, all the stuff is the same. P and Q, those are the logarithm of the prior density. And then for my likelihood, I call Poisson, which is the distribution we want to use for the data, log, which is the link function in this Poisson model. So mu is related to eta by logarithm if mu is equal to e to the eta. And then LPMF for logarithm of PMF for my observed outcomes, conditional on eta. And again, it's going to do some tricks for numerical stability in order to keep that from having numerical overflow. So everything is evaluated really accurately, and Stan can do this Hamiltonian Monte Carlo thing really well. So anyway, again, all I had to do was change like a couple lines to go from a Logit model to a Probit model. All I had to do is change a couple lines to go from a Probit model to a Poisson model. And that's because all of these things are just special cases of generalized linear models where you're relating conditional expectation of the outcome to the predictors via this inverse link function. And the inverse link function basically should assure that the conditional means are between the sort of lower bound and upper bound of the sample space for the outcome. So that's Poisson. Finally for today, negative binomial. Probably going to have to read through this at home. But there's a little additional step here where the conditional expectation the going into a Poisson is actually drawn from a gamma distribution. So we talked about the connection between negative binomial and Poisson a few weeks ago. And basically it's just a compounding of a Poisson likelihood with a gamma prior on the conditional expectation. And so that I can implement with my prior predictive distribution. I can also implement it to condition on observed data to update my posterior beliefs about the intercept and the slope. So just to jump to an example that you can do with rstanarm, this is a data set. It's actually an experiment on roach abatement. So there's a data set called roaches. There was some like new anti-roach treatment being administered to some buildings, but not others. So we want to estimate a negative binomial model for the number of roaches found at the end of the experiment as a function of whether it got no treatment or treatment and some other stuff, such as like how many roaches there were at the start of the experiment divided by 100. That's one thing that you do kind of want to do with generalized linear model is put your predictors in reasonable units. No one is interested in like what's the effect of a one roach change. So put it in units of 100 or 1,000,000 or whatever would be reasonable for like roaches in an apartment building. Specify some other stuff. I'm running out of time, so I can't go into a great deal about this, but here I'm just using the default priors and QR equal true. I get back this estimates and you're like, okay, the treatment is negative, has a negative posterior median, and it's like 4 times bigger than the standard deviation. It seems like it works, but you know, if you're talking to a exterminator, you don't want to be talking about posterior median of like linear predictor or anything like that. They're not going to understand you. So instead, you want to create one of these plots, which still may not be at the level of exterminator, but it reaches a larger percentage of the population. We want to just make a copy of our data set and then artificially set the treatment variable to 0, say control. Obtain the distribution of mu under our posterior distribution with the posterior linpred function, which gets the linear predictor and then transforms it into the conditional mean. So that's what we would predict for the conditional mean if all of the buildings were under control. Then we change treatment to 1, which is to say hypothetically now make all the apartment buildings treated. They get the new experimental treatment. Do the same thing, except now we've changed treatment from 0 to 1. And now we get these matrices, which are S by N, for what we would predict the expected number of roaches to be under treatment and under control, even though these are both hypotheticals. And so we specify new data in order to reflect that, but that's totally fine. And then you can summarize that treatment effect however you want it in terms of roaches, units of roaches, or in this case, relative roaches. So I did y1 minus y0 divided by y0 to sort of give me relative units. Anyway, here's the posterior CDF of that treatment effect. And so we have uncertainty about the parameters in addition to uncertainty about roaches. But you can say, okay, the posterior median of the treatment effect is probably to reduce roaches by 53% or something like that. But we're looking at the whole implications of the posterior here, so reflecting our uncertainty. But in any event, there's a very small probability that this treatment increased the number of roaches. So it looks like it is, an effective thing or whatever. Okay, out of time. I will post the third homework assignment tonight. It will be due Thursday before class, utilizing rstanarm. If you haven't picked up the reading yet, I highly suggest you do that. I have a few more copies here. If you have questions, post on CampusWire. Do the reading for next week, which will be using rstanarm more, but exploring other implications that you can do with those models. So we'll just pick it up there.